There's some debate on the internet about this physical phenomenon. How is this ball levitating, especially to the side? Is it because of the Bernoulli principle or the Coanda effect? In this video, you and I are going to walk through demonstrations of the Bernoulli principle and the Coanda effect, and then use what we see to explain how the ball stays suspended in air. We start our investigation with Bernoulli's principle in two very well-known experiments. The first is to create an airstream above a piece of paper and then observe the outcome. As you can see, the paper will rise up to the bottom of the airstream, where there is a low pressure region. Bernoulli's principle states that an increase in the speed occurs simultaneously with a decrease in pressure. Yep, it's in here. Here is a second demonstration, where two balls are side by side with a gap in between them. If I blow a burst of air at either one of them, it will be propelled backward. However, if I blow a burst of air between them, they will be sucked together, which is counterintuitive unless you know about Bernoulli's principle. The atmospheric pressure all around pushes the balls from all directions before the airstream. But with the airstream in close proximity, a low pressure region develops and the balls are pushed towards it by the surrounding atmospheric pressure. So the key idea is that as the velocity of the fluid stream increases, there's an inverse relationship with pressure, which decreases along the streamline. Now let's have a look at the Coanda effect. Conventional wisdom states that if we put an object in front of a blast of air, that air will not reach what is behind the object, as the blast will be deflected. Coanda, through a series of experiments, observed that the conventional wisdom was incorrect for sufficiently rounded or convex surfaces. The Coanda effect is the observation that when a jet of fluid is passed over a curved surface, it bends to follow the surface, entraining large amounts of the surrounding fluid as it does so. Here is a demonstration that shows the Coanda effect going in both directions around the cylinder. You can see how the primary, or top jet, actually wraps more than 90 degrees around the top of the cylinder. Here is a common demonstration claimed to be due to the Coanda effect. However, it is not. This is actually related to the teapot effect, something we'll look at in a later video. So the key idea is that the jet stream can attach and stay attached to a sufficiently curved surface, allowing it to bend with the surface for some given length before it detaches. And this effectively redirects the stream up to the point it detaches. Now that you know the key parts of each principle, which principle do you think is keeping the ball suspended in midair? Here is a demonstration using Schlieren imaging created by Harvard that I've added some overlays on to show the physics occurring. The imaging shows changes in density, which are clearly visible from the jet stream. And from Bernoulli's principle, we can identify the low pressure streams. We also see the wrapping of the primary and secondary jet streams around the ball, which is the Coanda effect. There are a lot of physics going on in this simple demonstration that we've glossed over and neglected, like turbulence, boundary layers, viscosity, and some others. However, the primary one appears to be that a jet stream is created and it imparts a force on the ball, which starts to push it up. Now, that jet stream is at a high velocity, so the pressure within that jet stream along the center line is low compared to the atmospheric pressure all around the ball. And so it's this atmospheric that pushes this ball up and keeps it attached to the low pressure region of the jet stream. And then that force from the jet stream, from momentum transfer, keeps the ball suspended. And both of these forces are counteracting gravity. The smaller jet clearly shows the Coanda effect. The top jet shows a very slight Coanda effect, but mainly a full jet stream. I'm going to conclude that the essence of the argument, whether it's the Coanda effect or the Bernoulli principle, is in favor of Bernoulli, because it's the jet stream and its high velocity and low pressure that is really counteracting the forces of gravity on the ball. And it's the momentum transfer of the jet to the ball that is counteracting the rest of the way. But I'd love to hear what you think. Do you agree with me? Or are you in Camp Coanda? Before we conclude our investigation, I have one more demonstration for you. Until now, we have used very smooth balls. Here's a lumpier ball, albeit symmetric around each axis. And my final question is, do you think this spiky ball can levitate?